So in this video I'm going to cover two examples relating to power, current, voltage, and above you can see the formulae from the previous video. It's the formulae for current, voltage, power, and the fact that the sum of all the powers in a circuit is equal to 0. Okay, so the first example I'm going to do says a constant current of 3 amperes flows through a light bulb for 15 seconds. The bulb emits 2,500 joules of heat and light or energy. Calculate the voltage over the bulb after 15 seconds. Okay, so we seek the voltage. So what do we know about voltage? So voltage is equal to the change in the energy over the change in Q. Okay, so what are we given? We know that I equals 3 amperes. We know T equals 15 seconds from there, and I equals 3 amperes from there. And we also know that W equals 2,500 joules of energy. Okay, so what do we have in this formula? We want voltage and we only have W, we don't have Q, so we have to work out Q somehow. So we say, okay, we know Q appears in I, and we are given I, and we are given T. We are given I and T, and we have to work out Q. So I equals change in Q over the change in T. So what do we have? We have I is 3, and we want Q, and we have 15 seconds. So if I take the 15 up, we get 45 coulombs for Q. Remember, the unit for Q is coulombs. Okay, so now we have W and we also have Q, so we can work out the voltage. So W is 2,500 over 45 from here. That gives us 55.55 volts. Okay, and that's the first example. The second one is a graph that is given, a power graph. But don't worry too much about the shape. It looks complicated in the beginning, but it's just to confuse students. So it gives us this. It's a power versus time graph, and it says power of an element is given from 0 to 10 seconds. Calculate the energy used from 4 to 10 seconds. So from 4 to 10. So we never even look at that part. Okay, so they want the energy used. So what do we know? We know from here, power is equal to dW dQ times dQ dt. If we cancel those dQs, because we don't have Q in this case, we get dW dt. Now from there we can say, okay, we want W, the energy, so how can we get it by itself? We can integrate both sides with respect to time. Then the derivative of this will just be W, because a derivative and an integral cancel, so it will be the integral of the power dt. So what do we know about an integral? An integral is just the area under the curve. So what that means is we can add this area with this area with this area from 4 to 10 seconds like that, and then we'll get the integral out. So that's from there. I'm going to add this area to this area to this area here. And the reason I'm doing them in different colors is because the magnitudes differ, the power magnitudes differ. So it'll just be easier to add them in the end. Okay, so if we have to add these, then we're going to get, sorry, wrong pen. We get the integral from 4 to 10 of the power dt is equal, let's put it this side, is equal to W, and that is equal to, so now we just add the areas up. So we take the area of the blue, so we know that this is a height of 2, multiplied by the width of this block. So that's 6 minus 4. 6 minus 4 gives you 2. Okay, then we add the next one. So we say it's 7 minus 6 times minus 1, because our height here is minus 1. Note that we go below the x-axis. So that would be minus 1 times 7 minus 6. If you'd like to write it out like that, you can write 1, but just for completion. So then this one also negative, and it has a height of minus 2. So minus 2 times 10 minus 7. Okay, so then we add all of this up and we say this is 2 times 2, which gives us 4, plus 7 minus 6 is 1, times minus 1 gives us minus 1, plus minus 2 times 3 is minus 6. And our final answer, minus 7 plus 4 is minus 3 joules for energy. And those are the two examples based on current, voltage, power. Thank you.